So I think we can start the lecture. There are 22 participants, that is including me. And yes, I understand that we have electricity problem in various parts of Mizoram. So if you have internet issue also, it's okay. I totally understand. But please type your attendance. I will upload the lecture video again. So, but I suggest that if you can, if you don't have an internet issue, you stay in the class. Okay. So I'll start from here. So yesterday we talked about Hall effect, and now today we'll talk about PN junction. So a PN junction, as the name suggests, it is simply like a system in which you join one type of semiconductor with another type of semiconductor. Like earlier we talked about p-type semiconductor and n-type semiconductor. So if you join them together, so what will happen? Now we know that in n-type semiconductor, for every arsenic atom or any other pentavalent atom you introduce, like this. So this is in the silicon crystal, one covalent bonding here, another covalent bonding with another silicon, for example, another covalent bonding with another silicon, another covalent bonding with another silicon. And in addition to the 4 electrons contributed to this covalent bonding, it has one free electron, right? So when you have a n-type semiconductor, for each donor atom, that is pentavalent atom, there will be free electrons. So you can assume that n-type electrons to be consisting of large quantity of free electrons like this. So if this minus sign represents the free electrons, if this represents the free electrons, you can picture an n-type semiconductor as a semiconductor where you have large quantity of free electrons. However, in a p-type semiconductor, as we discussed before, if you put trivalent atom like this in a silicon crystal matrix, so covalent bonding, covalent bonding, covalent bonding, and for the fourth one, it does not have sufficient free electrons in the valence electrons. So it does not have sufficient valence electrons. So there is a vacancy here. Okay, hole or vacancy. So vacancy is like deficiency of electron means in general you can consider it as a positive charge, even though it's not actually a positive charge, deficiency of electron simply. So vacancy or hole, each acceptor atom or trivalent atom, acceptor atom or trivalent atom contributes one vacancy, and p-type can be considered as uh, that semiconductor where you have large quantity of holes. Now, if you make a junction between p and n-type, we know that one side is having large concentration of free electrons and another side is having large concentration of holes or large deficiency in electrons. So if you join these two systems, definitely you know that there is concentration gradient, means there will be a diffusion, right? Concentration gradient means there is a diffusion. So I think you have learned about this gas molecules in two chambers. Suppose you have two chambers, I think you have learned the diffusion system. If suppose you have two chambers where you have, in one of the chambers where you have large concentration of gases, that is gas molecules with high pressure. High pressure means there is a large concentration of gas molecules, and another one is vacuum. Now, if you open this partition here, pull it up, then these gas molecules will diffuse towards the vacuum region. So exactly that same phenomena will occur here. There will be an electron diffusion from left to right, and you can consider that there is a hole diffusion from right to left also. So this diffusion will result in what is called transfer of charge. Okay, electron is transferred from left side to right side. That means there is a specific direction of transfer of charge. So if there is a specific direction of transfer of charge, then there it will result what is called diffusion current. Diffusion current. Okay. So this is another term that I would like to introduce here. So because of the concentration gradient, there is a transfer of charge in a particular direction, that is electron from left to right and holes from right to left. So there is a electron diffusion current, hole diffusion current also. I hope you understand this point here. We call it current because it contributes direction rate of change of current, rate of flow of charge. So there is a transfer of charge, means there is a specific current. So earlier, very often I talk about thermal energy. So under thermal energy, electrons and holes, they will move randomly in various directions because thermal energy does not have any preferential direction. Okay, heat, we know that it's a scalar quantity, so it does not have any preferential direction. It will go in various direction, and there cannot be any specific direction of transfer of charge. So if there is no specific direction of transfer of charge, then thermal energy cannot contribute to current. So that's why we never talk about thermal current. We never talk about thermal current. Okay. But here in this case, because of the concentration differences here, there will be a specific direction of transfer of charge, that is electrons from left to right, that contributes to electron diffusion current, and transfer of charge holes from right to left will contribute to hole diffusion current. Okay. Now, when the diffusion occurs, so let us go to this next picture here. So let's say this is the junction. So the dotted line is the junction. Dotted line is the junction. So in this dotted line, so when you join the two like n-type and p-type here, we know that each trivalent, sorry, this is your pentavalent atom. This is your pentavalent atom. Okay. Each pentavalent atom has one free electron like this. Each pentavalent atom has one free electron. And when you join with p-type region will have what is called trivalent atom. So each trivalent atom will have a vacancy like the one shown here. Each trivalent atom will have a vacancy. So when you join these two, suppose this is your partition dotted line. As there is a large concentration of free electrons on the left side and deficiency of electrons on the right side, this pentavalent atom having extra electron will find in its neighbor, that is the periphery, when you join the two type of semiconductor, right? This is the junction. When you join the two types of semiconductor, pentavalent atom having one extra free electron will donate its electron to this vacancy here in the trivalent atom. So by diffusion process, it will transfer these free electrons to the neighboring this trivalent atom. So when this pentavalent atom transfer its electron, that means it loses one free electron. If it loses one free electron, this atom, which was neutral atom, becomes once after losing this, it becomes positive ions. Okay, so if an atom, neutral atom, loses one of the electrons in the outermost orbit, it becomes positive ions. We know that, right? Now, this gallium also, trivalent atom, it will gain one free electron from the neighboring arsenic atom, pentavalent atom. After accepting one free electron, this trivalent atom will become negative ions. Trivalent atom becomes negative ion. So when you form a junction like this is the dotted line is a junction. So at the periphery of this junction, pentavalent atoms in the n side will transfer its free electron to the p side, and after losing the electrons it becomes positive ions. After gaining one free electron it becomes negative ions. Therefore, in this periphery of this junction here, the free electrons will be depleted. Free electrons will be depleted, and the pentavalent atom, after donating one free electron, we call it donor atom. Trivalent atom, after accepting one free electron from the neighboring pentavalent atom, we call it acceptor atom. They are negative ions. Here, donor atoms are forming a positive ions. So this region is known as depletion region, and this is also called space charge region. The reason why we are calling it a depletion region is that in this region we do not have any free electrons or holes. So it is depleted of free electrons and holes, so depletion region we call it. But it forms positive ions which are stationary in the crystal matrix, in the silicon matrix. See, it forms chemical bonding with the neighboring silicon atom. So this arsenic atom cannot move. After donating one free electron, it becomes positive ion. So you have a positive ion, you have a negative ions. They are charged particles, but they cannot move. Okay, so this region of space will have charged particles which cannot be moved. So therefore, we call it space charge region also. Oh, hello, nu hello. Class cái này log. Hello nghe. Hello. Class cái này log à? So so this is a very crucial region in a p-n junction. Not only that, this is considered depletion region because of that depletion of free electrons and holes. It is also a space charge region because it consists of positive and negative ions, immobile charges. Okay, positive and negative ions are immobile charges. They cannot move because they are embedded in the silicon crystal here, like this, with all this covalent bonding around it. They are, although positive and negative charges, they cannot move, and they cannot contribute to these positive and negative charges, like the positive ions and negative ions here. They cannot contribute to any electrical current because they are immobile. They are embedded in the charge. Okay, so we talk about free charges as well as the stationary charges, because these ions are stationary, they are not movable. So even though you say that there is a positive charge, negative charge, but they are not movable and they cannot contribute to electrical current. Okay, so for the fact that they are not movable, they will now form what is called electric field in this junction region. They will now form electric field in this junction region. What is going on? Oh, hello. Be a clock on low class. Can I make to not so no? So, uh, yeah. So in this region, once we have these positive ions and negative ions, they will now stationary charge here, positive ion, stationary negative charge here. They will now build up an electric field along this direction, positive to negative. They will now build up electric field like this. So in the periphery of this junction, again, there will be some other arsenic atom, which will also donate one free electron to gallium atom. Arsenic becomes positive ions, gallium becomes negative ions, and these stationary charges will build up electric field in this direction. Okay. Now, uh, here you see that there is a negative ions on the p side of the junction. This is the p side, and on the n side of the junction there will be a positive ions. Now, if we have some other arsenic atom here behind this arsenic atom, if this arsenic atom also tries to donate its electron to this gallium atom here, so by diffusion, if these electrons try to move towards this gallium atom here, the already built-in electric field, that is negative ions here, positive ions here, will now repel the incoming electrons. If the electron is traveling in this direction, the built-in electric field, which is as a result of these negative ions on the p side, they will repel electrically. They will give a repulsive force to this incoming diffusion electron, and uh, uh, eventually, when more and more positive ions and negative ions are formed at the periphery of the junction on the n side and the p side, the repulsive force created by this potential barrier or the electric field here, it will be sufficient to prevent further diffusion of the free electrons to the p side. So initially, when very few electrons diffuse, very few positive and negative ions will be formed, and such small number of positive and negative ions may not be sufficient to repel the incoming diffusion electrons. So eventually, it will create more and more positive ions on the n side and negative ions on the p side. Then uh, eventually, you will have sufficient electric field in the junction region. That sufficient electric field will prevent any further diffusion of electrons. So that is called equilibrium state of a p-n junction. So an equilibrium will be attained in which you have a specific region where the donor atoms donates its free electrons to the acceptor atom on the p side, acceptor atom on the p side. So there will be a certain specific region of length. That length on the p side and the n side is called depletion region. So this is a junction. On the n side, you have certain depletion region. On the p side, also you have certain depletion region. And in the depletion region, there is already a built-in electric field. And here we call this region here, the blue region, we call it neutral N region. Why do we call it neutral N region? Because in this region, there is a arsenic atom or pentavalent atom and its associated free electron. There is an arsenic atom and its associated free electron. So that means these arsenic atoms, they do not lose the free electrons. So electrically, they are neutral. And similarly, here in the p side region, the brown region here, it's called neutral p region. Here also, for every acceptor atom, that is the trivalent atom, there is always a vacancy. This acceptor atom has not received any extra electron. So if it has not received any extra electron, this acceptor atom is still electrically neutral. electrically neutral, right? So this region is the neutral p region. Okay, so we now talk about the depletion region, where you have a positive ions and negative ions and a built-in electric field. And you have in the n region, you have a neutral n region. In the p region, you have a neutral p region, for the fact that they have not received or they have not donate the electrons. Okay, so this arsenic atom will have equal number of electrons and protons. A gallium atom will have equal number of electrons and protons, unless it accepts the one extra electron, or unless it donates one extra electron. They will remain electrically neutral. So in the region which is still a little bit farther away from this junction, you have a neutral p region, neutral n region, and in the depletion region, of course, you have a positive and negative ions, and there is a built-in electric field. Okay. So by looking at this, so in this depletion region that we now call it, let's say there is a built-in electric field. Okay. So now, before that equilibrium is attained, we know that there is a diffusion current because of the diffusion of electrons to the p side. Also, once you have an electric field here, under the action of this electric field, suppose you have free electron here within this depletion region, under the action of this electric field, electrons will also tend to move towards the positive ions, away from these negative ions. Okay, so let me talk about this a little bit more in detail. So unless and until that equilibrium is attained, there can be some diffusion current. Also, because of this electric field, there can be what is called drift current. Drift current, diffusion current as well as drift current. This is something you should understand. Drift current means, I think I have talked about drift current. In a semiconductor, if you apply electric field, or if you connect a semiconductor to external battery source, under the action of this battery or under the action of electric field, electrons will move. Suppose this side is positive, this side is negative. Under the action of this electric field, electrons will move. So when electrons move under the action of electric field, the motion is called drifting, and the current contributed by the transfer of charge under the action of external electric field is called drift current. Okay, so similar to that, in this depletion region also, we have positive ions region, negative ions region, and there is an electric field. So if you have certain charge like electrons and holes here within this depletion region, those electrons and holes will also tend to move under the action of this electric field. So when they moves under the action of this electric field, we call it electron drift current and hole drift current. And when the equilibrium is attained, the number of electron current due to drifting and the diffusion electron current, they will be equal and they will cancel out. So there cannot be any further transfer of charge from N side to P side. Okay, so when equilibrium is attained, let me repeat, the drift current and diffusion current, they will nullify each other. As you see in this depletion region, the drift current and the drift current and the diffusion current, they are in opposite direction. Here, diffusion current, as we talk about it, it is mainly due to the difference in concentration. It diffuses towards the p side. But once you have a built-in electric field, electrons will tend to move in opposite direction to the diffusion current under drifting here. So electron under reaction of this electric field will drift in the opposite direction. So when we talk about this electron diffusion and electron drifting, when equilibrium is attained, when there is when this electric field generated due to this positive and negative ions are sufficiently large, uh, drift current will cancel out diffusion current, and the overall current across the p-n junction will become zero. Okay, that's what I want you to understand. And the subsequent discussion will be quite simple once you understand the actual phenomena that takes place in this p-n junction. Uh, I think I will stop here today. So up to that point, if you want to raise anything, any clarification you need, because here it will be subsequent calculations and all. So all these calculations I will explain. I think I can finish in tomorrow's class. Up to this point, I will try to finish in tomorrow's class. That is the potential barrier calculation. So up to this point, yeah, let me just show you this figure also. Here, on the left side, we are writing p-type. On the right side, we are writing n-type. We know that the majority charge carrier in p-type is holes. The minority charge carrier in p-type is electrons. So this subscript p here represents the material p-type, p-type. So pp means the concentration of holes in the p region, which is the majority. Np means the concentration of free electrons in the p region, that is the minority charge carrier. Here Nn means, subscript N means the n-type region, n-type region. Nn means the concentration of free electrons in the n region. In n region, due to the high doping concentration, that is the large concentration of donor atoms, the number of free electrons is much greater than holes. Therefore, electrons are majority charge carrier in n-type, and holes are minority charge carrier. So if you plot the carrier concentration like this, you will find that here this is your pp, this is your pp, and this is your np. Here np, the concentration of electrons in the p region is very low. Concentration of holes in the p region is very high. However, when you come to the n-type here, concentration of free electrons in the n side is known as Nn. Concentration of holes in the n side is known as Pn. So Nn is majority charge carrier here, Pn is minority charge carrier in the n region. However, in the p region, pp, that is the concentration of holes, is much greater than the concentration of free electrons in the p side. So pp is the majority here, np is the minority here in the p-doped semiconductor. So this is the depletion region or space charge region. On the p side, after accepting one free electron, they become negative ions like this. They become negative ions. After donating one free electron, they become positive ions. So space charge region, this forms your depletion region. Okay, so this is how the electrons and holes concentration will vary over the p-n junction, and how the depletion region are formed. We will, in a subsequent class, we will calculate the potential barrier across this junction region, the space charge region, and also we will calculate the width of this depletion region. That's what we are going to do in the subsequent classes this week. Okay, so I will stop now, because if I start this session, this calculation, I don't think I can finish in 4 minutes. Tomorrow I will finish. So up to this point, if you have any queries, we still have 4 minutes. I don't want to do this mathematical step now, explain this mathematical step, because I have to define everything again tomorrow. So if you don't have any queries, I think I will stop here, or you have typed your attendance. Okay, good. I think you can exit the meeting. This is the probably your 5th class.
Thank you, sir.
Mm,
Thank you, sir.
be exhausting already. Okay, we'll stop.